Today we're going to use L'Hopital's rule to evaluate certain kinds of limits. Project 6 is due today. First, a little bit of history about L'Hopital. Right? This is all one guy's name, all this long thing. We just call him L'Hopital, okay? Yeah. And Marquis de Saint, yeah, that whole thing is his name. He was a French mathematician, late 1600s. He wrote the first European textbook on calculus, and wrote is in quotes because virtually the entire textbook was lifted directly from notes made by another mathematician, Bernoulli, another really famous mathematician. So L'Hopital paid Bernoulli to tutor him in calculus. Bernoulli was one of a handful of people in the world who knew this subject. And Bernoulli sent L'Hopital a bunch of notes on calculus, and he published them as his own. I don't know. Maybe, I don't know. I'll have to look into that. Okay, so we're going to take a look at these limits from the questions of the day. We're going to do each one 2 ways. One sort of an old way that we would have had to resort to before, and one using our new way. So the limit as x approaches 2 for this function here, as x approaches 2, the first thing you should always try when you're taking a limit is just plug in the value that you're interested in. Okay, so if I just plug in a 2 here, I get 3 times 2 squared minus 2 minus 10 over 5 times 2 squared plus 3 times 2 minus 26. So that's 4 times 3 is 12, minus 2 is 10, minus 10 is 0, and 20 plus 6 minus 26 is 0. And what do we say about 0 over 0? Undefined. It's an indeterminate form. Yeah, we call that an indeterminate form. So it just means we have more work to do. So we have done problems like this before, and the more work part meant try to factor and cancel, or do some fancy algebra to make it so that you can plug in a 2. So let's see, if this thing factors, we'd have 3x and x and 5x and x. All right, so let's see, does this factor? Uh, 3x squared minus 6x minus 6x plus 5x is negative x minus 10. Yeah, that works. And then this is going to factor to 5x. I don't know. What factors go into 26? 13 and 2. Let's put a 2 here and a 13 here. So that's 15x and 13x. That's not good. Oh, sorry, 10x and 3x. That could work. That's a 13. 10x and 13. Yeah. So the difference of 13 and 10 gives me the 3. All right, so that factors. All right, so that's nice. I have a x minus 2 in the top and the bottom. I can cancel those. Okay, and now I can try to plug my 2 in. 3 times 2 is 6, plus 5 is 11, and 5 times 2 is 10, plus 13 is 23. 11 over 23 is the limit. Sure. Good question. Let's graph it. Yeah, so this function, you're right, and this function are equal, except that this function you can't plug 2 into, and this function you can. This function will have a hole at x equals 2. This function does not. So they're exactly the same except for that single point. If you had an asymptote, you would never be able to plug in the number, no matter what you do to it algebraically. Yeah. Okay, so we got 11 over 23. So now I'm going to use a different method, L'Hopital's rule, to evaluate this limit. So with L'Hopital's rule, when you get 0 over 0, the reason it's an indeterminate form is because there's a question of which goes to 0 faster, the numerator or the denominator. If the numerator wins and the numerator is going to 0 faster than the denominator, the whole fraction is going to go to 0, right? But if the denominator wins, if the denominator is going to 0 much faster than the numerator, the denominator is going to go to 0 and the fraction will blow up. Or they could hit some kind of balance, right? Like they could be going at such a rate, the top and the bottom could be going at such a rate that they kind of balance each other out at some constant, 11 over 23. So you can get anything. When you have 0 over 0, you could get 0, you could get infinity, you could get a constant. And the reason you get what you get has to do with the rate at which the numerator goes to 0 and the rate at which the denominator goes to 0. And what mathematical tool do we have to measure rate? Derivatives. Derivatives measure rates of change. So I'm going to take the derivative of the top and the derivative of the bottom, and that's what L'Hopital's rule says you can do. The limit as x approaches 2, the derivative of my numerator is 6x minus 1. The derivative of my denominator is 10x plus 3. Okay, so notice I am not doing the quotient rule here. I'm not taking the derivative of the quotient. L'Hopital's rule, we're not trying to take a derivative of the quotient at all. We're just trying to take a limit. And L'Hopital's rule says that if you want to take a limit of a fraction, you can take the limit of the derivative of the top over the derivative of the bottom. And now that I've done that, I can plug my 2 in. And 6 times 2 is 12, minus 1 is 11. 10 times 2 is 20, plus 3 is 23. I know, right? All right, so here's another one. Same function, same exact function, but this time I'm taking the limit as x goes to infinity instead of as x goes to 2. So what happens to this guy as x goes to infinity? The end behavior of that rational function. It goes to 3/5. Yeah. Don't need, oops. I don't need L'Hopital's rule at all here. Yeah, so we had this rule from pre-calc that when the degree of the numerator and the degree of the denominator are the same, then the limit, the end behavior is just the ratio of leading coefficients. That in this case it's both, but we're just looking at x goes to positive infinity in this case. Yeah. Okay, so that's the old way. But if I wanted to use L'Hopital's rule, right? I know that from a pre-calc rule, right? But if I actually tried to plug in infinity, right? The limit as x goes to infinity of 3x squared minus x minus 10. What happens to the numerator as x goes to infinity? It gets really big, yep. And the denominator as x gets close to infinity also gets really big. Infinity over infinity is another indeterminate form. It is impossible to know what happens when you end up with a limit that looks like infinity over infinity, unless you have some special rule, right, that we have derived. The infinities can't cancel out. Yeah, it all has to do with which one goes to infinity faster, right? If the numerator goes to infinity faster than the denominator, the whole fraction is going to get big and go to infinity. If the denominator goes to infinity faster than the numerator, right, then the denominator is going to get bigger faster than the numerator does. That whole thing's going to go to 0. If they go to infinity at exactly the same rate, it would go to 1, right? or it might balance out at some other constant. So we use L'Hopital's rule again. L'Hopital's rule says that if you have something that looks like 0 over 0 or infinity over infinity, when you're trying to take a limit, you can take the limit of the derivative of the top and the derivative of the bottom, and it will be the same thing. So this would be 6, oops, didn't mean to write an equal sign there. The limit as x goes to infinity of 6x minus 1 over 10x plus 3. And what happens to 6x minus 1 as x goes to infinity? Goes to infinity. My denominator, 10x plus 3, still goes to infinity. This is not helpful, so do it again. So the limit as x goes to infinity of no. Well, yes, that's what L'Hopital's rule says, because, yeah, it says, look, the denominator is going to infinity a little bit faster than the numerator. Yeah. You just keep taking derivatives until you can get an answer. The limit as x goes to infinity of 6/10 is 6/10. Yeah. Yeah, if you had a 10th degree polynomial in here, you might have to take 10 derivatives. Yeah. So this technique works for general limits of indeterminate form of the type 0 over 0 or infinity over infinity. And it's called L'Hopital's rule. So this is just the formal statement of L'Hopital's rule. It says that if you want to take the limit of f of x over g of x and you're getting 0 over 0, you can take the limit, the same limit of f prime over g prime, and you'll get the same answer. Same thing for plus or minus infinity. Okay, your turn.